Okay, great. Well, thank you and welcome to my talk on data-oriented design for differentiable probabilistic programming. This is joint work with Maria, Younesse, and Sam. So this talk is one of the reviewers described this talk as kind of like a functional Perl style talk, which I actually thought was I didn't think of it in that way, but it's kind of accurate. Which is that this talk is basically about a technique or a trick for taking a data structure that was originally formulated in a lazy language, Haskell, and making it work in a strict language. But the why do we care about this? Well, the overall motivation is that the data structure in the lazy language was is the key component for LazyPPL, which is a probabilistic programming language for non-parametric statistics. So, like backing up a couple layers, I want to start by talking a little bit about why do we care about non-parametric statistics. So what is non-parametric statistics? It's kind of a confusing name because there is still a parameter space conceptually. It's just that sampling from the parameter space calls rand unboundedly many times. So it's the parameter space is just not Rn. That's all it means. So an example of this would be piecewise linear regression, where when you do piecewise linear regression, you're sort of trying to fit data points with a piecewise linear function, but you don't know ahead of time how many pieces. And in theory, it could be unboundedly many pieces. So that's why it's a non-parametric problem. So why non-parametric statistics? Well, in typical Bayesian inference, you sort of take a fixed model and you infer its parameters. But what if you are unsure of the model? So in epidemiology, we have these things called Petri nets, which represent sort of they're models for epidemiological processes. They involve like populations and transitions. And you can take one of these models and try and infer its parameters. But what if you want to infer the model? Well, then you need a non-parametric statistics approach. And also, if you're doing stochastic differential equations, when you have an adaptive SDE solver, it might call rand. You don't know how many times it's going to need to call rand. So now I'm going to get into the data structure. To give motivation for the data structure, I'd like to contrast LazyPPL with a classic Haskell PPL. There are several Haskell PPLs which sort of work on this basic design, which is that you have a probability monad and it's given by the state monad over a list of doubles. And so uniform here would just take the first list of doubles. And you do this so that you can in Metropolis Hastings or Hamiltonian Monte Carlo or et cetera, you can sort of vary the doubles as you do MCMC. The problem with this is that when you sequence things, the first thing has to complete fully before the second thing can run, because you have to know how many things the first thing ate. So the LazyPPL gets around this by having a different monadic composition. So now prob kind of looks like the reader monad, but notice that it uses split. Instead of passing the same tree into both processes, it splits the tree and passes one thing into the first and the second thing into the second. We'll talk about exactly how tree and split are defined in a couple slides. So here's an example, though. What does it look like? Well, we can sample a linear function by sampling its slope and its y-intercept. Then we can sample a stream of linear functions, a lazy stream. So this will only, it'll keep using things as long as you actually ask for them, but it won't give the whole list up front. And sort of the great thing about LazyPPL is that like even though this linear stream needs like infinitely many um, random values, you can still sequence them. So you can have two linear streams, and because they're sort of working off of independent halves of the tree, they won't interfere with each other in a way that they would for the sort of the traditional PPL design. So how does this work? Well, it's this tree is this thing called infinite rows trees. So basically, an infinite rows tree consists of a double and a stream of infinite rows trees. And then a stream of infinite rows trees is just the classic. It's like a cons list without the nil case. And this is what it looks like to split. So you take it, you can cut off the first thing in the stream and return that as one tree, and then take the double from the tree and add it to the rest of the stream to make a new tree. Okay. How do we actually make these? Well, you make these, you can sort of lazily construct an infinite rows tree starting from a splittable random number generator. So if the random number generator has this interface, you can make a uniform random number from it, and you can split it. Then you can create a rows tree by these two mutually recursive functions. One creates a tree by sampling a uniform and then sampling trees. And the other creates a stream of trees by sampling a tree and then sampling a stream of trees. Crucially, with different random number generators. The thing to note for later is that sort of, if you imagine a lazy thunk, which has over rand tree or rand trees, it only has to close over the random number generator. Okay. Now we're gonna take the lazy data structure and make it work in a strict language. We're also gonna make it work more efficiently with data-oriented design. Data-oriented design is a term that I think comes out of video games, but it's basically just kind of a philosophy for how to make things go fast. And how do you make things go fast? Well, you use memory in a way that is easy on your CPU caches. So you put similar things nearby to each other, and you make your data structure small. So I'm going to show how to use these principles to transform the lazy data structure into a high performance strict data structure. So the first thing is, well, we have trees and we have streams of trees. So let's put, instead of spewing these all over the heap, let's put these in vectors. And this looks like this. Now, this first take one doesn't actually work because we have no thunks. So this would have to be an infinite thing. But the basic idea is that we have these trees, and then they point into the tree streams by index, and then the tree streams point into tree and tree stream also by index instead of pointers. Now, to add the thunks into the mix, we can sort of manually implement the Haskell thunks by having, remember that the state of the closure for the thunk is just a random number generator. So we can store all of the states of those closures in a vector, and then a thunk either points into that vector for the unforced case, if it's an unforced thunk, or it points into either trees or streams when it's forced. So then we just take the same structs as before, and instead of having indices here, which are usize, we put thunks. Then the last step is to make thunk really small. So here, if you do the calculation, thunk turns out to be 16 bytes. Here it is 4 bytes. That is 4 times smaller, which is great. And then we also do a array of structs to structive arrays translation, so that which also for alignment issues that just makes everything more compact. This is another like wisdom from data oriented designs. So instead of having a vector of structs, we take each field and put it in a separate vector. And what does this look like to actually use? It's actually, I won't show all of the techniques, but we can wrap this in a fairly ergonomic interface to use from Rust that essentially just involves passing around this tree pointer struct. You can call this tree pointer trawl.normal, and it'll sort of sample normal random variables, and you can also split it. This sort of takes advantage of Rust's ownership system, where if I passed the tree into this first sample lin, I wouldn't be able to use it for the second. So instead, I sort of split off, which also mutates the tree in place, so that I can sample twice. And actually, it turns out with some clever things that I won't get into, you can replicate some other things from the Haskell, like the piecewise linear functions. Okay, so is it faster? The big question. Well, we're pretty sure. Basically, we've tried Metropolis Hastings on piecewise linear functions. The Haskell version runs in 5 minutes. The Rust version runs in 2 seconds. I think that's pretty good. But benchmarks are hard. Apples to apples comparisons are also hard. The Haskell might be doing slightly different things, so we have to figure it out. But preliminarily, it looks pretty good. But more importantly, when I look at the profile, the managing the tree is not the majority of time. The majority of time happens in the actual sampling and Metropolis Hastings algorithms. So that's good enough. The other thing is that beyond whether it's faster or not, it enables this technique from LazyPPL to be used in more traditional scientific languages, which have libraries for ODE solving, autodiff, etc. So Rust and also C++ and Julia. And it opens the door to algorithms which you need to iterate over the observed sites. Because in Haskell, you can't tell whether a thunk has been forced or not. But now you can actually introspect and tell whether the thunk has been forced. And in the future, so we have already, in fact, integrated this with a reverse gradient autodiff engine. I don't have time to go into that. On top of that, we hope to integrate it with Hamiltonian Monte Carlo, but non-parametric Hamiltonian Monte Carlo is still an open research question, which I think Maria will give a talk on. Either she's already given it or she will give it. And then the final extension would be to use this data structure in the backend engine for a high-level DSL, which the Rust interface is already fairly ergonomic, but it would be convenient to not have to pass around the tree pointer everywhere. So that's it. Thank you.
Owen, thank you. So are there any questions in the audience? Maybe. Okay. I can ask a first question.
Yeah.
So, okay, I think you kind of covered it, but I mean, the abstract says the thing, the work was motivated by aiming, you were aiming to reduce memory usage and things like that. So have you achieved these memory reductions? Or maybe another way of asking is were you, did you have some theoretical expectations about the sort of memory reduction you can achieve with this sort of thing before starting the work? And did you see these actually sorts of reductions? Sorry, I'm my jet lag is hitting me. I have to let you know. Yeah.
So I would say that there's sort of two sources of memory reductions.
Yeah.
One would be the actual sort of sorry, there's a bit of echo. The one source of memory reduction would be that it's the tape itself is smaller in memory. But another source of memory reduction is that we can reuse the tape memory for successive runs in MCMC. So in LazyPPL, there's sort of unbounded, or it's the garbage collection can't. You either have to garbage collect the old things, or if in LazyPPL, often they end up being held onto by garbage collection. So when you have it in Rust, you can actually have you can guarantee that it's constant memory usage over the MCMC run, as opposed to Haskell, where if you get lucky, it might be, but there's sort of always bugs there. So I would say of the two things, the second one, where you can guarantee over the course of MCMC that the memory use is just constant, that's more important than actually. I mean, having the memory be smaller means that it fits into cache more, which is great. But the second one, I think, is the more important thing.
I think there are like a couple of questions. Maybe the
Yeah, hi, this is Steven. So I had a question about exactly what Rust's ownership model is doing here. So, I was curious because you have this splittable resource here, this random number generator. And in Rust, you need to be very careful about this, especially if you have a mutable resource and you're splitting. And I was just curious, to what extent did Rust's ownership model agree with or not agree with how you were manipulating the resources as they flowed through this?
That's a great question. So there's actually unsafe happening here under the hood, because these pointers are like, when I split it, it's actually pointing mutably into the same structure as the old pointer. But it's like I make the interface so that the sort of only mutation of the structure is evaluating thunks. So even though it looks like there's concurrent mutable accents, like it's actually fine. So Rust's memory model was actually, or like ownership was actually a hindrance here, because I did have to drop down to unsafe. But once I only exposed these safe operations, then the ownership was kind of nice, because it enforces the fact that you have to split when you call a subprogram, which is like, it doesn't have monads, but you can enforce that the monadic composition from Haskell is what you have to use when you're calling subprograms, which I thought was kind of interesting.
Thank you.
Thank you.
Hi, Owen. Thanks for the talk. So one part of what makes lazy people lazy is the use of these rose trees. Because if you tried to use a different randomness monad in Haskell, then it would have, inside of the monad, you'd have to resolve things in sequence. But another part is just that Haskell is lazy, which means that user programs can do things like use infinite data structures and stuff like that, which is what a lot of the examples in that affine monads paper were sort of getting at. So how could you program like that in your Rust DSL? Is that a goal of this project? And if so, have you thought about how to get that sort of user-facing laziness into the language?
Yeah. Is that Alex, by the way?
Yes.
Okay. I can't see you, but I can recognize your voice. Hi. So that's a great question. The answer is yes. Basically, you can make like lazy data structures, which so for instance, let's say like a lazy infinite list of normal random variables. You can do that by storing having a struct that stores a pointer to the tree, and then sort of uses that subtree, that pointer, that it's subtree, to like get more stuff on demand and memoize them. So it's like a struct that you can it has a vector of like the things that it's already got in it. And then if you ask for something that it hasn't got yet, it'll just like expand the vector until it gets that, and then return that. I don't know if that made much sense, but it does work.
Cool. Thank you.
Thanks. I think this is all the time we have for questions. Thank you very much again, Owen. Let's thank Owen one more time, please.